Recall the real valued function of n variables. So we had a coefficient by x1 plus another coefficient by x2 and so on up to Cn xn. This real valued function is called the linear form on Rn. Now in contrast, if we have the x variables raised to the second power plus c2 x2 squared and so on up to Cn xn squared plus a summation of I equals 1 up to n minus 1 and j equals I plus 1 up to n, and we're summing a coefficient ij, and that's multiplied by xi, xj. So here I is always less than j. So essentially we take xi xj as being equal to xj xi. So we'll just multiply this expression by 2, and this will become clear in some examples. But essentially, these are called the cross terms or cross product terms. And this entire expression is the quadratic form on Rn. And what we'll do is take these coefficients as C11, C22, and Cnn, and we'll see why this is convenient when we write it in matrix form. Now the general quadratic form on R2 is C11 by x1 squared plus C22 by x2 squared and plus 2 by Cij, so that will be 1, 2, by x1, x2. So as we can see in this case, n is equal to 2. So therefore we're summing from I equals 1 to 1 and j equals 2 to 2. And we only end up with this term. And similarly, the general quadratic form on R3 is C11 by x1 squared plus C22 by x2 squared plus C33 by x3 squared, and then we have 2 by C12 by x1 x2 plus 2 by C13 x1 x3 and plus 2 by C23 x2 x3. Now it's convenient to express these quadratic forms in matrix form, being a vector x transposed by a matrix A by x. So the quadratic form on R2 can be expressed as x1 x2 by the matrix of coefficients. So we take the coefficients of the squared terms and put them on a diagonal, and we take the coefficients of the cross terms and put them off the diagonal. So essentially we have 2 of C1 C2 So we put each separate C1, 2 in row 1, column 2, and row 2, column 1. So this matrix A is symmetric. And then we multiply this by x1, x2. And similarly, for the quadratic form on R3, suppose we had, for example, 2x squared plus 3y squared minus z squared minus 5xy plus 3xz plus 4yz. So we take x transpose, having components x, y, z, and our matrix A will be a 3 by 3 in this case. So on the diagonal, we put the coefficients of the squared terms, so 2, 3, and minus 1. And off the diagonal, we put half the coefficients of the cross terms. So in row 1, column 2, we have minus 5 on 2. And in row 2, column 1, we have minus 5 on 2. And in row 1, column 3, we have 3 on 2. And row 3, column 1, we have 3 on 2. And row 2, column 3, we have 4 on 2. And row 3, column 2, we put 2. And that's multiplied by our vector x, having components x, y, and z. So in general, the quadratic form associated with A is equal to x transpose by A by x. So as we saw, A is an n by n symmetric matrix, and x is an n by 1 column vector. So transposing it gives a 1 by n row vector. Now in addition, if A is a diagonal matrix, then we put lambda 1 to n on a diagonal and zeros off the diagonal. So essentially in this case, we'd have no cross terms and only squared terms corresponding to the entries on a diagonal. So we'd write the quadratic form as follows. So we'd have x being transposed, multiplied by the diagonal matrix, and multiplied by x. So that would give lambda 1 by x1 squared plus lambda 2 by x2 squared, and so on up to lambda n by xn squared. The principal axis theorem enables us to do a change of variable to come up with an equivalent quadratic form with no cross terms. So essentially, if a matrix A is a symmetric R by R matrix, then there is an orthogonal change of variable that transforms the quadratic form, being x transpose by A by x, into another quadratic form, being x dash transpose by a diagonal matrix by x dash. So we're changing variables from x to x dash. So essentially, if a matrix P orthogonally diagonalizes A, then the change of variable x is equal to p x dash in this quadratic form yields this quadratic form. So to show this, we can substitute for x. So we have px dash transposed by A by px dash. So that would give x dash transpose by p transpose by A by p by x dash. So if P orthogonally diagonalizes A, then this matrix will be a diagonal matrix. So we end up with x dash transpose by D by x dash. And therefore, given our R by R symmetric matrix A, this new quadratic form will be equal to lambda 1 by x1 dash squared plus lambda 2 by x2 dash squared, and so on up to lambda r by xr dash squared. So these lambdas are the eigenvalues of A that correspond to the eigenvectors that form the successive columns of the matrix P, as we've seen. So these eigenvalues will be on the diagonal of the matrix D. So as an example, if we write this quadratic form in matrix form, we'd have x1, x2 with the coefficients of the squared terms on a diagonal, and the off-diagonal terms will have half this coefficient. So we'd have -1 and 1, which correspond to the cross term. And that's multiplied by x1, x2. So again, to find the eigenvalues, we take the determinant of A minus lambda I which is equal to 0, being a characteristic equation. So we'd have 1 minus lambda squared minus 1 is 0. So that would give lambda squared minus 2 lambda plus 1 minus 1 is equal to 0. So if you factor this, we'd have lambda 1 is 0 and lambda 2 is 2. So therefore we can write our quadratic form as follows, with a change of variables. So we have x1 dash x2 dash by the matrix D with the eigenvalues on a diagonal. So we'd have zeros off the diagonal. So if you multiply this out, our new quadratic form will be 2 by x2 dash squared. And q dash is equal to q. And I'll leave that for you to verify as an exercise using the matrix of orthonormal eigenvectors P. Recall that the conic sections can be formed by cutting a plane through a cone or a pair of cones with a common vertex. And if the cutting plane went through the vertex, we'd get degenerate conics. So in general, the quadratic forms in 2 space, being ax squared plus 2bxy plus cy squared plus dx plus ey plus f is equal to 0, where a, b, c are not all 0, represents a conic section. Now if d and e are both 0, so there's no linear terms, we end up with ax squared plus 2bxy plus cy squared plus f is equal to 0. So this represents a central conic. Which includes circles, ellipses, and hyperbolas. So these have axes of symmetry. Now furthermore, if b is equal to 0, then there are no cross terms. So we'd have ax squared plus cy squared plus f is equal to 0. So this also represents a central conic, but in standard position. So for example, if there were cross terms, then this ellipse in standard position would be rotated. So the central conics in standard position includes ellipses and hyperbolas with their foci on either the x or y axis. So for example, you may have a hyperbola that looks something like this. So in this case, the foci would be on the y axis. So we can write our central conics in the following form, being x transpose by a matrix A by the vector x is equal to R. We're taking f to the right hand side, gives R is equal to minus f. So the central conic in standard position, with no cross terms, can be written as xy, and the coefficients of the squared terms go on a diagonal, and we have no cross terms, so we have 0 off the diagonal, and that's multiplied by xy is equal to R. And the central conic with cross terms can be written in a similar way. So we have xy by the coefficients of the squared terms, again on a diagonal, and the coefficient of the cross term, being 2b, is divided by 2 and placed off the diagonal. And that's multiplied by the vector with components xy is equal to R. So you can actually evaluate this product and verify that you get this central conic. And the 3D analogues to the central conics in standard position are central quadrics, in standard position. And now we'll look at a method for identifying what kind of central conic we're dealing with if it has cross terms. So it can be rotated. And this is best illustrated in an example. Suppose we have this quadratic form and we know it's a central conic, being in the form ax squared plus 2bxy plus cy squared is equal to r, where r is equal to minus f. But we don't know what type of central conic it is. So what we do is write this in matrix form. So we have xy by the matrix A with the coefficients of the squared terms on the diagonal, and minus 4 on 2 gives minus 2 for the off-diagonal terms, which corresponds to the cross term. And that's multiplied by xy is equal to r, which is 14 in this case. So what we do is a change of variable to obtain an equivalent quadratic form with the variable x dash. So we have x dash transpose by a diagonal matrix by x dash, where x is equal to the matrix P that orthogonally diagonalizes the matrix A by x dash, being our new variable. So here we solve the characteristic equation for our matrix A to obtain the eigenvalues, which we've done before, and then substituting these eigenvalues into the equation A minus lambda I by the vector v is equal to 0, we can find the basis eigenvectors for each separate eigenspace that corresponds to each separate eigenvalue. So we've done these steps previously. And in here, we've normalized each eigenvector by dividing each component by the norm of the vector. So I'll leave this part for you to do as an exercise. And therefore this matrix P has the eigenvectors in each column. So we have 2 on root 5, 1 on root 5, and then minus 1 on root 5, 2 on root 5. And you can verify this is an orthogonal matrix by taking the dot product between both column vectors and both row vectors, which should give you 0. So the eigenspace corresponding to V1 is one-dimensional, so it's a straight line. And this eigenvector is the basis vector for that eigenspace. So this is eigenvector V1. And the other eigenspace is also a straight line that's orthogonal to the other eigenspace. And the eigenvector V2 spans this eigenspace. And recall from the principal axis theorem that this matrix D is P transpose by A by P. So if you evaluate this product using matrix A and P, you should get D being equal to the diagonal matrix with the eigenvalues 2 and 7 on the diagonal. So now if you evaluate this product, you'd get lambda 1 by x1 dash squared plus lambda 2 by x2 dash squared. And that's equal to r, which is 14 on the right hand side. And now if we divide through by 2 and 7, the 2's cancel and the 7's cancel. And we'd have 14 on 2 by 7 on the right hand side, which gives 1. So therefore, if we take the square root of 7 and square it, and the square root of 2 and square it, we see that this is a rotated ellipse where the length of the semi-major axis is root 7, so the vertex of the ellipse has coordinates of root 7, 0 in our rotated coordinate system, and the length of the semi-minor axis is root 2, so this point has coordinates 0 and root 2 in our rotated coordinate system. So this here is x dash, and this is y dash. And you can find this angle using trigonometry. So we take tan theta is equal to the vertical component of the eigenvector, which is 1 on root 5, on the adjacent component, which is 2 on root 5, so we get 1/2. And arctan 1/2 gives an angle of around 26.6 degrees for our rotated ellipse. If we have a quadratic form Q being equal to x transpose by A by x, where A is a symmetric matrix, then this quadratic form is positive definite if Q is greater than 0 for all x except the 0 vector. And the quadratic form is negative definite if it's less than 0 for x not equal to 0, and it's indefinite if Q has positive and negative values. Now following on from this, if A is a symmetric matrix, then the product x transpose by A by x is positive definite if and only if all eigenvalues of A are positive. And similarly, x transpose by AX is negative definite if and only if all eigenvalues of A are negative and the quadratic form is indefinite if A has at least one negative eigenvalue and at least one positive eigenvalue. Now consider our quadratic form, which was x transpose by A by x is equal to a constant r, where r is not equal to 0. Then if we divide through by r, we get the following form. And if there were any cross terms in this quadratic form, we'd do a change of variable to eliminate them and obtain the following equation, with the first eigenvalue by x dash squared plus the second eigenvalue by y dash squared is equal to 1. So in this case, the eigenvalues 1 and 2 are the eigenvalues of the matrix A divided by the constant R. Now if A is a symmetric 2 by 2 matrix, then the quadratic form x transpose by A by x is equal to 1 represents different conics given the following conditions. So if A is positive definite, meaning both of its eigenvalues are positive, then the quadratic form represents an ellipse. And this can be seen from this equation, which is representative of an ellipse if both of these values are positive. And now let's make a bit of space. So the second condition is that if the matrix A is negative definite, meaning both eigenvalues are less than 0, then a quadratic form has no graph. So given the squared terms, if both of these eigenvalues are less than 0, then you can never get 1. And if A is indefinite, meaning both eigenvalues have opposite signs, then we see the quadratic form represents a hyperbola. So given our example here, through a change of variable, we found the following equation, and the length of the semi-major axes of the ellipse and the semi-minor axis of the ellipse in our rotated coordinate system. So alternatively, we can rewrite this quadratic form, and dividing through by 14, we have 3 on 14, and 6 on 14 would be 3 on 7, and then we have minus 2 on 14, which is minus 1 on 7, and minus 1 on 7. Multiplied by xy is equal to 1. So this is our matrix. So to get rid of the cross terms, you'd find the eigenvalues of this matrix. So these would be 1 on 7 and 1 on 2. And because the eigenvalues are both greater than 0, then our matrix is positive definite. And therefore our equation here, lambda 1 by x dash squared, so we'd have x dash squared on 7 plus lambda 2, which is a half, by y dash squared, is equal to 1. So we can see that root 7 squared and root 2 squared in the denominator gives the same equation for the ellipse that we obtained earlier. Using the alternative method of finding the eigenvalues of A, but here we have an alternative method to be able to quickly classify our conic sections using the eigenvalues of this matrix A on R corresponding to the quadratic form, where the right hand side is 1.